Okay, so again, this is the inflation, this idea of inflation, which, of course, as all scientific ideas had a lot of resistance at first, but now it's almost commonplace in the thinking of cosmology, of especially the Big Bang theory. It's now been very strongly incorporated because of what it does as far as solving the problems with the Big Bang theory. All right, so that's this amount that the universe expands by, in a nonlinear manner. It's actually expanding, by the way, if you look at the actual equations that describe this, the universe during this time is actually expanding faster than the speed of light, which seems, it seems wrong that can be taking place, but it turns out that there's nothing in relativity that prevents the universe from expanding faster than light, basically information cannot travel faster than the speed of light. So this is a very short period, as it says here, from 10 to the minus 43rd to 10 to the minus 35th seconds. This is the time where the universe undergoes this non-linear inflationary period, it's what's considered a quantum fluctuation. The energy from the vacuum of space gets used up in a nonlinear way in expanding. It all goes into expanding the universe very, very rapidly. Anyhow, this is a theoretical idea, although it does seem to explain a lot of things. All right, it corrects for this problem with the horizon and also flatness, and it also does a couple of other things for us. This inflationary. Well, I mean, these are the main things. All right, I don't want to really go off into too many tangents. I would like to get done, hopefully, with this chapter by the end of this video, or hopefully before that. All right, so this is they're showing you let's see. So this diagram shows how the horizontal problem is solved. The points that are opposite from each other were in fact in contact with each other, right before inflation. So this is, when the universe is extremely small, they were in contact. So that's that problem. The flatness problem, basically here I thought this was a clever description. So suppose you take an ant, right? So an ant is, maybe a centimeter or so in size, or usually probably less than that, maybe like half a centimeter in size. But if the ant is on a balloon that has a radius of 10 centimeters, the ant can see the curvature very easily, right? Not a problem. But if the balloon here, which represents the universe, is blown up, 10 to the 50th times in a really short amount of time, the ant, which is still, the same size, will roughly see that the universe appears locally, and even actually in any direction the ant looks, would look relatively flat. All right, and so that's the problem. That solves this problem of this flatness problem that we encounter nowadays. That of course somehow the critical density is exactly the match that is needed to keep the universe flat. So basically, the universe looks flat, as far as the eye can see, because of this very early expansion, this nonlinear expansion, also known as inflation. All right, so that's that solves that. Let's move on. So before decoupling, the background radiation was kept from clumping. So this is a huge idea in cosmology. If the background radiation, right, what we now see as the cosmic microwave background, of course it's in the microwave now, but back then it wasn't, back in the early universe it certainly wasn't, unless there is clumping, that is, there's areas in the universe which are hotter than other regions, then you're never ever going to form galaxies and stars and clusters of galaxies and things like that. It just wouldn't happen if the universe was completely, exactly the same, right? And the very early studies of the cosmic background radiation, so going back to 1964 and shortly after, it seemed as though the microwave background radiation was absolutely the same. Like there was no differences whatsoever in that, and so the question became, how do galaxies form? How do you get stars forming? You need some kind of tiny differences in the background radiation, or at least we expected to see these tiny differences. All right, so the background radiation basically does not clump before decoupling, right? So remember, decoupling is about 400,000 years after the Big Bang, remember, when decoupling happens, that's when the photons, which were very, very close to the visible spectrum, when decoupling took place, the universe was roughly 3,000 Kelvin in temperature, and of course cooling off as the expansion continued. But before this happens, this decoupling, basically the universe was essentially very, very, very uniform. But variations in the density of matter before decoupling would have led to variations in the cosmic background radiation. But we didn't see any, right? In the early days, and even decades after. And there were different teams, of course, that went looking for this cosmic background, these variations, these slight variations in temperatures, but didn't find it for a very, very long time. All right, so of course the story is we needed spacecraft to go and look for this, to get above the atmosphere and to basically perform the same experiment that Penzias and Wilson performed, but with a much more sensitive instrument. Let's see. So as it says here, galaxies and quasars must have been forming around when the universe had a redshift of 6, and possibly as long ago as somewhere between remember, the redshift is greater than 1. But relativity takes care of that, right? So meaning greater than 1, of course, the redshifts are meaning that the universe is, the recession velocities are greater than the speed of light, but we can take care of that using the theory of relativity. And actually, there's a lab on this, as you're going to see. That's the Quasar lab. All right, so anyhow, let's see. So the overall expansion of the universe, any clumps we should see some kind of clumpiness. And in fact, we think that this really has to do with the dark matter, right? So dark matter is not affected by electromagnetic radiation. At least we don't know about any kind of effect we've been looking for this to see if there's any kind of relationship between radiation and dark matter, but there doesn't seem to be. But anyhow, the dark matter seems to be where galaxies. So the clumping of dark matter seems to be where galaxies are going to form. All right, so this is just kind of a vision of the early universe where dark matter and normal matter are spread out. The dark matter starts to get clumpy. They pile up in certain regions, certain parts of the universe, and where over time, where the dark matter is you find clumps, you're going to eventually gravity will draw in the normal matter in those directions, and that's where we're going to see galaxies. All right. Well, nowadays, of course, what we've seen is the dark matter surrounds the galaxies, but in the early, it really might have to do with the formation of galaxies in the first place. They're going to be attracted to the dark matter. So from our large-scale structure of the universe, we see that roughly 4% is normal matter, 23% is what's called cold dark matter. There's some argument for hot dark matter as well, but it seems to be cold dark matter is the dominant form of dark matter. Anyhow, that we're not really don't need to go down that road. And then 73% of the universe seems to be this thing called dark energy, right? That accounts for the acceleration of the universe. Remember, that amount hasn't changed since the beginning of the universe. So, as I said, we were trying to find these little variations in the cosmic background radiation. In around 1990, there was a satellite called COBE, the Cosmic Background Explorer, and it found slight variations. As you can see, the blue regions are cooler, the yellow to greenish regions are slightly hotter, and those are the ripples that we expected to find in the background radiation. This is kind of where the dark matter accumulates and where normal matter will eventually gravitationally attract to. Later on, after COBE, the success of COBE, we sent another spacecraft up. When was this? It was at least a decade or so. I think it was in the early 2000s. This was called WMAP, and WMAP gave us a much more detailed view of the cosmic background radiation. The red is really the hotter regions. The blue are where the voids are going to form. So remember, this is the cosmic background radiation as seen roughly 400,000 years after the Big Bang. All right, so I actually finished. I didn't think I was going to make it to the end of this chapter, but that is it. All right, so that's that. Here's the summary. You guys can look at that. Pretty much just what I covered. All right, so that's it for Astronomy 102. There is another chapter, by the way, in the textbook about chapter 28, but we cover that in Astronomy 101. It has more to do with the possible existence of life in the universe, besides on the Earth. And all right, so I'm going to end it here, and all right.